Okay, welcome to week 8. Week 8. 8, 9, 10, 11, 12. There's only 5 more weeks left. And we've got a lot to get through, so I better talk faster. Okay, no tutor lab classes this week. I'm surprised anyone turned up actually, because I thought everyone might think quiet week. No classes, no lectures, no tutors, no labs. But it's good that you made it. Alright, so as we reach the pointy end of the course, we start having exams. So there's a prac exam, which because of the gigantic size of the class has to run over 2 weeks. So some people will be doing it this week, some people will be doing it next week. The aim is to work out whether you know how to manipulate arrays. Now if you've been working on the assignment, surely you've already worked out how to manipulate arrays. In fact, you've worked out how to manipulate matrices. So the exam should be a stroll in the park. So there are going to be 3 small-ish programming problems which you have to solve in 1 hour. Andrew's not expecting everyone to get full marks for this, so if you can only solve 2 problems, that's fine. He's expecting everyone to pass, or he's rather hoping that everyone's going to pass, but not everyone is going to get a high distinction. But as many of you as can, it would be nice if you solved all those problems. There's some revision exercises for practice. If you have problems with the revision exercises, there are some revision labs that are running this week, so go along to them. Alright, the assignment's due on Sunday, probably. You should assume that and work towards that. You should have started this a while ago because the assignment was released a couple of weeks ago. Just in time coding does not work in COMP1511. If you leave your assignments to the last minute, you're going to end up in a mess. So you should always start early and gradually work towards getting a solution. And kind of some of the stuff that I've been doing in lectures where I do a simple version and then I extend it and extend it and extend it is probably the way to go. And the thing that Andrew wants you to do is to submit your code every time you make some changes. Now, not every semicolon, but every time you sit there for an hour or so and make some changes to your code, submit it. And it's going into, Give is going to put it into a Git repository. And you'll be dealing a lot more with Git later, but just for this exercise or for this course, just using Give puts it into Git, and you can always use Git to get it back if you want. You can get help on the forum. Don't post code on the forum. You can email the tutor. Since you don't have, it's interesting, the last 2 weeks we haven't had lab and tute classes, so you haven't really had much contact with your tutors, but you could send an email and you could also go to the help sessions. So this week, what we're going to talk about is searching and sorting, 2 very important operations in COMP1511. So let's get to work on them. Right, so searching is important because most of the time in computer science you're dealing with large amounts of data which is packaged into some kind of data structure, and a very frequent operation that you want to do is to work out whether a particular item exists somewhere in the data structure. Now I've mentioned a whole lot of different data structures here. The only one we've talked about so far is arrays, and that's what I'll be using in the example today. But all of these data structures contain collections of items, and a very common kind of thing to want to do is to work out whether a particular item is somewhere in the data structure. How you implement that depends to some extent on the kind of data structure. So the way you deal with lists is different to the way you deal with trees, it's different to the way that you deal with graphs. List, trees and graphs we'll be talking about a lot more in COMP1511. And also it depends to some extent on the kind of items you've got. For the sake of this exercise today, we'll simply be looking at arrays of integers. So we know how to compare integers. We've got double equals, less than, greater than, and so on. And arrays, we know how to manipulate arrays, hopefully by now. Alright, so two different approaches, even with the same data structure and the same kind of items. There are generally different strategies that you can use to try and find items in the data structure. And we're looking at two today, linear search and binary search. Now, binary search requires that the array is already sorted. It won't work on a non-sorted array, as I'll demonstrate in a moment. Linear search will work on anything, whether it'll work on any array. In fact, linear search is a very general kind of searching strategy. It also works on lists to some extent. Something like linear search will work on trees and graphs as well. But linear search is kind of the search of last resort. You don't want to use linear search if you can avoid it. And that kind of leads on to the next point about there's all these different ways of approaching searching. Is one of them better than some of the others? And the answer, as always, is it depends. Depends on the context. If you haven't got a sorted array, then you can't use binary search at all, for example. You can only use linear search. So if you've got a sorted array, then you've got a choice. You could use linear search, you could use binary search. Which one would you use? Well, we'll have a look at the performance characteristics of these two algorithms in a moment. Right, so let's start looking. Oh, I actually wanted the editor, and I wanted to open up search. Right, so for this exercise, I'm going to use a bunch of functions, or just two functions, for manipulating arrays. One of them will fill an array with various kinds of data, and we'll have a look at how it does that in a minute. And the other one will print out the first part of an array. The arrays we want to deal with, we don't want to just deal with trivial things like 10 or 15 items. We want to deal with 10,000 or 1,000,000 items and have the algorithms work on those kind of sizes. So I've got two functions, one that will fill up an array with various kinds of random values, and the second one will print out a slice of the array. Now, interesting thing about slices of arrays, basically they're just, so you've got an array, it might have 100 items in it. Say you're just interested in the part of the array from the 10th item to the 20th item. And we're going to call that a slice. And a lot of these algorithms work on array slices. So our printing array algorithm is going to work on a slice of the array. And always what we're going to do, we're going to print the first 15 items. And a lot of the time you can actually see that the array is tending towards what we want just from the first 15 items. Alright, so I've packaged those two functions for populating an array and printing an array in one of these libraries, and I've got an interface for it, but let's have a look at the code itself. Okay, so there are two functions. One is insert values, the other one is show values. So what insert values does, it populates an array of integers of size n, and it does it in a particular order, and you can specify what order you want. There's three possible orders. One is random order, one is ascending order, one is descending order. So in ascending order, the smallest element's first and the largest element is last. In descending order, the largest element is first, smallest one is last. In random order, they're just whatever. So how does insert values actually work? I'm not going to talk about it actually. I'll just use it and we'll worry about how it works later on, perhaps. And show values is basically just going to take part of, so we've got, it also assumes you're dealing with an array of integers, of n integers, and it picks out part of the array starting from a low index up to a high index and just prints out the values there. So the core of this is starting from low, going up to high, and printing out the next value in the array. Alright, so what our main program does is it takes two command line arguments, therefore we're expecting argc to be equal to 3, and the first command line argument is the size of the array, so we can specify how large an array we want, 10, 20, 100, 10,000. And the second argument is the order, which is going to be a single character, a single letter in fact, either R for random, A for ascending, D for descending. And so this piece of code here just checks that we've got three command line arguments, i.e. the name of the command plus the size plus the order, and it tries to extract the values of those two things, the size and the order, into two variables. And if it doesn't, then it prints an error message and fails. So hopefully there's nothing unusual there. One thing that you can see that I'm exploiting is C's, I keep wanting to say lazy evaluation of Boolean operators. So if this fails, or in fact regardless of this, the expressions will continue to be evaluated. So it's only going to continue if we actually have three arguments, and so on and so on. Alright, so once we've got the number of items in the array n, we then create an array of the appropriate size. So remember from last week, or from week 7, where we talked about malloc, creates a chunk of memory containing a certain number of bytes. The number of bytes is worked out here with a product. We want n items. Each item is that many bytes long. So an integer on most machines, and certainly the ones in the labs, happens to be 4 bytes long. So if we say 100, n is 100, we're going to get 400 bytes, which is enough to hold 400 int values. So effectively an array. Of course, malloc can fail. In our case, it's never going to fail because we're not asking for a lot of memory. Well, most of the time we're not. So that really should never happen. But always when you do a malloc, you should check whether the malloc was successful or not. Alright, we then call the insert values function to populate the array, and we display what's in it, and then we go into a loop where it just asks us to search for a particular value and tells us whether that value is in the array or not in the array. So normally the thing that we're searching for, we'll often call that thing a key. So we're searching for a key value in an array of n integers. That happens to be called numbers. So let's run it. Pick a size. Let's pick a small one to start with, and an array of 15 random values. Okay, now it's pretty, not super interesting to search for a value in an array so small, because you can always just look through and see if it's there or not. But if you can't be bothered looking through, let's say we want to check whether the value 7 is in the array, and it's not. We want to check whether the value 15 is in the array. Well, it's obvious that it is because it's the first element, and it's saying not found. Why is it saying not found? Because I just remembered I hadn't completed this function. So what we're going to have to do is we're going to have to write it. So in theory, for 15 it should have said found, and any of those numbers it should say found. Any other value that's not in that array it should say not found. Alright, so what are you doing? What are you doing? Normally, if I type anything that's not a number, it'll just stop, right? So let's go back to search 1. So the function that checked whether the value's key is stored in the array is called linear search. And it returns either 0 if the value is not in the array, or it returns 1 if the value is in the array. Alright, so here's our linear search function. Haha, no wonder it always tells you that it's not found, because it always just returns 0. Right, so this is the kind of function that you see in the prac exams, where there's just a dummy there that returns some value because this function is defined to be a function returning any. So we've got to return something, but we don't always want to return 0. All right, so this is the idea behind the linear search algorithm. Basically, you start at the start of the array. You look at the first element, is that the one I'm looking for? No, it's not. Go to the second, is that the one I'm looking for? No, it's not. Go to the third, is that the one I'm looking for? No, it's not. Da da da. Eventually you might find it, or eventually you might reach the end of the array and you haven't found it. So in which case you'd return 0. I have a diagram to illustrate that, or is it this one? So this is linear search. So I starts at the start of the array. Let's say we're searching for the value 20. Alright, so the critical operation that we perform here, for a given value of I, we check whether AI is equal to the key. 13 obviously isn't equal to 20. If it's not, we go to the next item. So is AI 7 equal to 20? No, it's not. So we go to the next item. Is that equal to 20? No, it's not. Go to the next item. Yes, it is. So at that point, we want to work out that we found what we're looking for, and we want to stop our scan of the array. And I'll take a look at a couple of different ways of doing that. Let's say we search for the value 2. Alright, so we're going to go back to the start. That's not 2, 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 da da da. And eventually I falls off the end of the array, and the loop that's scanning through the array stops. Okay, you've also, hopefully, over the break, you haven't forgotten that the standard technique for scanning through an array, I equals 0, while I is less than n, where n is the size of the array, do something with the current item, I equals I plus 1. Okay, so when that loop eventually stops, I is going to be equal to the size of the array, which means it's going to be 1 more than the last index in the array. So that's where I is going to end up if the value is not currently in the array. Alright, so that's the strategy. We want to render that as a piece of C. Right, well there's kind of two reasons why we want a loop to continue. One is that we haven't reached the end of the array, and the other reason we want the loop to continue is that we haven't found the value that we're looking for. We haven't found the key. So if we're going to scan the array, clearly we're going to have something like this. And I'll get lazy from now on and just start using I++ rather than I equals I plus 1. Alright, so that effectively does for each item in the array. Alright, we want to know whether the current item is equal to the key value x. And then we want to do something. There's two ways you can handle this. One of them is to introduce a Boolean variable that tells you whether you found the item or not. And so we could say, alright, if AI is equal to x, we found the value we're looking for, therefore found is true. So, oh, that was a mistake, wasn't it? So what's the initial value of found? Well, we haven't checked. We don't know whether the value's in the array. And so often what we do in these situations is we start by assuming that it's not in the array until we have evidence to the contrary. So I can do that. Okay, if I see it, then I flag it as found. Now, if I did this, then I'd scan the entire array, despite the fact that I may have found the item I'm looking for as the very first element. So I'd always scan the entire array. That's not such a great idea. You don't really need to keep scanning once you've found the item that you're looking for. So I could modify this continuation condition and say, while I haven't found what I'm looking for, and while the value of I is less than n, keep going. Right, so as soon as I find the item I'm looking for, then found will be set to 1, this will become false, and the loop will terminate. Otherwise, we'll keep going, and we'll keep going, and then another possibility is that we eventually terminate when I becomes equal to n, which it eventually will because we keep incrementing it, starting from a base of 0. Alright, so now we don't want to always return 0, we want to return 0 only if it's not found. Conversely, we want to return 1 if it is found. So and I could actually just mimic what's written up here, but I won't. I'll write it out in long form. Okay, so that will do the complete linear search. Start from the start of the array, scan through, element at a time. If you find the element you're looking for, set this flag, and that will, a side effect of setting that flag is that the loop will terminate. If you never find the element that you're looking for, found will continue to be 0, and the loop will terminate because that condition there will eventually fail. So once the loop's finished, we've got the indication of whether we found it or not in that variable. So that's one way to do it. Let's check whether that actually works. I've already set up my makefile to say. Alright. So we had 15 items in random order before. One thing about the way I'm doing these random items is that for a given size of array, it always generates the same set of items. So you'll always see those items appearing. If you make the array a different size, then it'll generate different items. That's just to make it a little bit consistent. So we search for 5. 5 is found. See, I didn't even look. I didn't realise it was there or not, but there it is. We search for 2. 2 is not found because it's not in the array. We search for 15, that's found. Search for 13, that's also found. And if we search for any of those values, it's going to say found. If we search for anything that's not in the array, it'll say not found. Alright, so that's one approach to implementing that. Any questions on that? Yep.
If you were to make an insanely long number that would actually roll over and it would reach 15 again, like it was that insanely big, would it be found?
How do I make an insanely long number? Are you saying an insanely large array?
No, so like you know how it would create an overflow or something if you were to, well, it wouldn't do that, it would create garbage if you were to put in a number greater than 2 to the 32.
Yeah.
So if you were to create a number that was twice that, and then you add 15 to that, so it would go past the negative numbers, with,
no. I'm not sure how overflow actually fits into this. It's really, I mean, unless you have such a gigantic array that n is larger than 2 to the 32, in which case, sure, you might have a problem. But in fact, I don't think it will fit in memory if you have such a large array. So it's not really an issue. I mean, you just you're scanning up to n. N can be 10,000, can be a million, whatever. And the only test that's happening is this equality test here, so this is not really an issue of overflow. Anyway, I don't think. But we can try. Let's quit from there. Let's run it again. Search from in an array of size 1,000,000. Might help if I use the correct name, and it might help if I gave the third argument. Let's do random ordering again. Right, so there's the first 15 items from my array of 1,000,000 items. Think of a number, 1, 2, 3, 4. Is that number in the array? Now this is where search becomes more interesting, because we don't know whether 1, 2, 3, 4 is in an array of size 1,000,000, and we can't be bothered looking through it, so we can just ask that to tell us. Alright, is 1, 2, 3, 5 there? Well, it turns out that it is. Happens to be in the array. If I printed out the whole array, eventually you'd see 1, 2, 3, 5 somewhere. It's 1, 2, 3, 6 in the array. No, it's not. Oops, got that. Then 1, 2, 3, 7 happens to be in the array, and of course I can search for a large number like that, and that happens to be in the array. I didn't know it was going to be there, but turns out that it is. So where does the overflow come into things, do you think?
So basically, if for example negative 2 to the 31 was in the array, if you were to type in 2 to the 32 plus 1, such that it would roll over.
Yeah, alright, yeah, sure. So I guess your point is if I type a giant number like that, then I'm not really searching for what I typed, I'm searching for some random value. Sure. Is that detectable? Yeah, there's probably a way of detecting that is a number that's too large, and then not searching at all in that case, because you don't know what you've got. But not really in general an issue in this context. Alright, so that's one way of doing it. Let's save that as search 1A. Good. Just let me. Let's get back in here. Right, so here we are back again with the linear search that we just typed. Right, so there's two reasons we want to break out of the loop. One is that either we find the item we're looking for, or the other one is that we hit the end of the loop. Now there's, thinking back to week 7's lecture, I talked about some additional control structures for changing the way that loops work. Right? We had break and continue. So here, we could actually do away with this found variable. And in general, the less variables you have and the less testing you have to do each time, we could do something like that. Okay? So as soon as we find the item we're looking for, we do a break. Now, that'll terminate the loop at a particular point when AI is equal to the value of X. But we've no longer got this variable, so now we need to think of a different condition down here for deciding whether to return true or false. Can anyone suggest what that condition might be? And I'll tell you one that's not correct. You might might say, well, you know, we can check whether we actually found the thing. Why isn't that going to work all the time? It'll work correctly if X is an element in the array, but if X is not in the array, what's the problem? When is the loop going to terminate? It's going to terminate when I is equal to n. When I is equal to n, is that a valid index in the array? No, it's not. So, this isn't a suitable way of checking whether we've actually found something, or whether we found X. Because in the case we don't have it, then we'll be beyond the end of the array. Yep.
If the return one inside the
Could do that. True. You must have been reading Andrew's code. So that's one possibility. And down here, if we ever reach this point, we reached it because we didn't find the value that we were looking for. So that'd be one way of handling it, and that's actually not a bad way, and it's probably the way people like me would write that code. As soon as you know whether you've found, or as soon as you know whether the key is in the array, you may as well just say yes, give the value yes back to the calling program. It's only if you reach this point down here, it's not really this issue at all. We're never going to get to this point if we don't find, we're never going to get to this point if we actually find the value X somewhere in the array. So we know that if we reach the end of that loop, it's because I is equal to n, and therefore we didn't find X. So we know to return 0. So that one, let's just try that one. Make sure it actually does work as advertised. Let's do 1,000,000 again, because that's slightly interesting. It's going to generate the same random set of things. So I think 1, 2, 3, 4 was not found. 1, 2, 3, 5 was found. Okay. So with that crappy amount of testing, I draw the conclusion that it's actually working. Let's try at least one more. How many 9s were there? 6. Okay, so that value's found, and it's not found. So, jumping to a general conclusion from those 4 examples, it seems that the code is working, and in fact it is. Alright, so the other suggestion that I was going to make with the break is that if we use a break here and we come down here, then what we're interested in, the way we can tell whether we've actually found an item, is that I is less than n. Okay? The only reason we'd exit that loop if we don't find it is that I is equal to n. And so we could say if I is less than n, return 1, otherwise return 0, or we could do something like this. Simply return the value of that expression. So if I is less than n, it's going to return true. If I is not less than n, it's going to return false. So that saves having to write an if statement. We simply calculate the correct return value at that point. So which of those is easier? I don't know. Maybe the return one is slightly simpler. Should just check though that this works. I haven't broken something. Not found. Found good. Found. reason I know that I can do that is because I know how the numbers are generated. In fact, it just generates numbers and then adds a random gap between them, which is a relatively small gap, either at 1 or 2 or 3. So even if something's not found, then the next item might be found, or the next value might be found, or the next value might be found. And so on. Alright, so that's all very nice. One thing that we might be interested in finding out is how much it's costing us to do this. And I've written another program which actually takes that code that we looked at and instruments it to add some things to count the number of comparisons that we do. Search 2.c. Right, everything up here in the main program is all the same as the one that we looked at before. The only difference is that down in the linear search function we add an extra variable to count the number of comparisons that we make. And we know that every time we enter this loop, we're about to do a comparison again of the key value x against the current array item, so we know that there's going to be an extra comparison there. So if we use our random array of 1,000,000 items again, and we search for 1, 2, 3, 4, we do 1,000,000 compares before we discover that it's not found. And anything that's not found is going to require 1,000,000 comparisons, because we always have to scan through the entire array before we can work out that the value that we're looking for is not there. 1, 2, 3, 4, 5, well, we happen to find that value partway along the array, so we only needed to do 30,000 comparisons there. What if I search for this number here? One comparison, because it happened to be the first item in the array. What about 1, 2, 3, 4, 5, 6? If I search for that one, so that requires a lot of comparisons because it's close to the end of the array. Okay, we don't know anything about where the items are likely to appear in the array, so it's pretty hard to work out in advance, given a particular key, how many comparisons it's going to take. And the number of comparisons is generally important because while here we're just doing simple integer comparisons, sometimes we can be doing string comparisons, and they're quite a bit more expensive than a simple integer comparison. Also, that's the comparison of AI against X is kind of the critical operation in this whole thing. It's the one that's going to be executed on every iteration of the loop. So I wanted to quickly think about the cost of doing linear search. I had another function, another file where we can start recording things like that. Now, what's the best cost? In terms of number of comparisons, it's always going to be 1. If the key we happen to be searching for happens to be the first item in the array, it doesn't matter how big the array is, it's going to take one comparison, whether it's 10, 100, 1,000, or 10,000, or 1,000,000. Maybe I should crank that up a bit. What about the worst case? And here we're assuming random ordered array. So the worst case is always going to be the number of items in the array. You look at the first item, it's not that. Look at the second, it's not that. You look at all of the items, and the key that you're looking for isn't any of those items. So one thing to notice about this, as the array gets larger and larger, the cost of doing binary search grows larger and larger. What about on average? This one's tricky because we don't know what's in the array, and so you can't really analyse anything precisely. You could come up with an estimate and say that, well, on average, we're probably going to look at half of the values in the array before we work out. If the item is in the array, we'll look at half the values. Now, then we've got to assume how likely is it that we're going to search for a value that is in the array, and how likely is it we're going to search for a value that's not in the array. And then you can take those two likelihoods into account, and you can come up with a kind of plausible thing. But often we'll just say, as an estimate, that it's roughly, we search roughly half the array before we decide that we found the item that we're looking for or not. Now obviously that's not quite true, because most of the time you happen to be searching for items that aren't in the array, then the average is going to be skewed more towards n than it is to n over 2. So, as I've said, it's an estimate. And that applies to all of these as well. So if you start thinking about the numbers, you know, this is 10,000 comparisons to work out the worst, in the worst case. This is 5,000 comparisons in the worst case. So the cost of doing linear search grows linearly, surprise, surprise, hence the name linear search. Okay, well, let me see, 1150. All right, so let's take a look at another kind of search. Oh, why am I doing that? This is the one I want. Linear search, binary search. All right, here's an approach to searching that we can use if the array happens to be sorted. We can do the kind of thing that you might do with a phone book or a dictionary if you were doing a fairly dumb approach to searching for a word. If the word starts with M, you know it's roughly in the middle of the dictionary. If it starts with A, you know it's near the start. If it starts with Z, you know it's near the end. Right, assuming that we don't have that kind of information available, what we can do is we can say, all right, let's take a look at the midpoint. And let's say we're searching for key value 8. No, let's search for something that exists. Alright, so if we look at the midpoint value, remember the array's in order. If the key that we're searching for is less than the midpoint value, well, we know for sure that it can't be in that part of the array. But it could be in the first half of the array. So what we do is we move our attention, and you can kind of think of this as focusing. We focus on the first half of the array. And then we repeat that process. Find the midpoint, which is, if you look at the formula here, low plus high, so high is 3, low is 0. 3 divided by 2, remember that it's integer arithmetic, so it's going to round down. So the midpoint is going to end up being here. And then we can check, does that value equal the key? And in this case, yes, it happens to. So that took 2 comparisons, plus a bit of address calculation. What's that square bracket to work that out. Now, it turns out that if we'd done linear search, it would also have taken 2 comparisons to find the result. What happens if we're searching for, rather than 7, if we're searching for 17? So we're going to start out assuming, well, it could be anywhere in the array. Let's go to the middle and compare that value to the middle value. Now, in this case, it's greater than the middle value, so it's going to be somewhere up here, if it's in the array at all. So once again, we compute the midpoint. Damn! Alright, it's going to work out. First thing we do, so we say, alright, it can't be in the lower part of the array, so we'll refocus our attention to this part of the array. And then, alright, looking here, where's the midpoint of that part of the array? Using the formula here, it's going to to be 8 plus 5, 13, divided by 2, it's going to be 6. So we're going to look there. I should have searched for something different. Maybe oh, no, I won't. I'll just search for that. All right, and once again, we find it in 2 comparisons. Okay. So all we had to do was compare against 14 and then compare against 17, and we had our solution. Now, if we're doing linear search, we start here, 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 here. So we've done 6 comparisons to get to 7 comparisons to work out. Okay, so it's clearly a bit more expensive. Now, in such a tiny array, who cares? It doesn't matter whether you use binary search or linear search, but once you get to larger and larger arrays, it makes a significant difference. What if we were searching for 20? So I would have, after the initial thing, I would have said, all right, 20 is greater than 14, so we focus on the top part of the array. Let's get the midpoint, that happens to be right there, again. And so 20 compared to 17, okay, well 20 is greater than 17, so we refocus to this part of the array and recompute the midpoint. The midpoint happens to be here, which happens to be low, and then we'll discover 20. What happens if we're searching for 18? So we would have got to this point, we would have computed this as the midpoint, we would have discovered 18 is greater than the midpoint, so we would have moved that up. And then we discover, compute the midpoint. Once again, it's here. 18 is less than the midpoint. So we say, well, it can't be above 20. So possibly it's below 20. So we actually move high down to here. And then we discover that high is less than low. So they've crossed over. And effectively, that means we focus down to nothing. So there's no slice of the array left that we can consider to look for 18. So as soon as they cross over like that, or if they're equal, and if high happen to equal low, which can happen depending on how many items there are in the array. If you get to the point where you've got one or no items to look at, and they're not equal to the key, then you know that the item doesn't occur in the array. Okay, so at that point there, we would have worked out 18 is not in the array. So that's binary search strategy. So focus your attention to half the, or cut out half the remaining part of the array each time until you eventually either hit the item that you're looking for, or until you reduce the slice of the array to nothing, or to one element that doesn't contain the key that you're looking for. Alright, so after the break I'll show you how to implement that in C. Okay.